Good afternoon to one and all present here. I welcome all the participants to this Phase 4 6 days short term training program. Now we are going to start this fourth day and second session. Once again, thank you for joining with us. Now let me introduce our resource person, Dr. C. Mary Esther Ma'am, Hambledon postdoctoral fellow, Indian Institute of Materials Physics, University of Munster, Germany. She has completed doctoral degree in nanotechnology in 2018 at VTU Belgaum. Her research interest areas are reversible electronic state transition, transparent electronic technologies, thin films development for electronic applications, amorphous substrate interface analysis. She has acquired many professional achievements. Here are the few glimpses. Alexander von Humboldt Postdoctoral Award from Germany from October 2019 to till date. Research Fellowship Award, Indian Space Research Organization from 2013 to 2018. She has received a patent on transparent resonant tunneling diode and its preparation methods. Patent from German. Welcome you, ma'am. We are honored with your presence, ma'am. The current session topic is functional behavior of oxide film and characterization challenges for smart and futuristic applications. Now I request our resource person to proceed with the session, ma'am.
Yeah, it's a wonderful introduction actually. Thank you so much. So,
Thank you.
shall I start my presentation now? I hope
Yes,
I
ma'am. Yes,
can.
ma'am. You
If
can
any
share the
technical,
PPT. We will check it, ma'am.
yeah, sure.
Yes, yes, ma'am.
I hope this is fine. Shall I continue?
Yes, ma'am. Yes, ma'am. Please, ma'am. Please.
Yes. So first, I would like to thank so much for this wonderful opportunity, and thanks for the participants. And good afternoon to everyone. This is me, Carmel. I am postdoc research fellowship, received Humboldt fellowship from Germany, and now working as a scientist in WWO Germany. So today I prefer to talk about functional behavior of oxide thin films and characterization, and especially the major challenges. And I would like to give some few ideas for futuristic applications also. So before beginning, I would like to introduce my institute. So Institute of Material Physics has several facilities. So among that, I would like to point out two important characterization facilities, that is transmission electron microscopy, which is also included in situ transmission electron microscopy facility, and the next one is secondary ion mass spectroscopy. Most importantly, we have also radioisotope and diffusion studies lab. So I have two important collaborating experts, Professor Gerard Wilde and Sergei Devinsky. So with their help, I am now pursuing my postdoctoral fellowship. So you people might have come across many different explanation for functional behavior of material. So here I would like to give different kind of definition for the functional behavior of material. So if we see the satellite, we can immediately understand it is wrapped up with several type of different materials. So first, golden color, the glittering wrap up is by multi-layer insulation. So this is a aluminized kapton layer which is stacked into several layers, means that is why it is called as multi-layer insulation, and it wrapped up. And further, interestingly, we can see few places is covered with optical solar reflector. This is basically by doing several simulation understanding where the satellite is facing too much heavy sunlight load. Those places will be covered by optical solar reflector. But the disadvantage is the the internal surface will face heavy cooling. So there we must require to incorporate some active heating elements. Of course, we cannot use the MLI and optical solar reflector on all the surface of the satellite. For example, if we see the antenna of the satellite, it is covered with germanium black polyimide. Why it is so? Because the aluminized kapton layer will may as a act as a barrier for RF. Like RF means radio frequency has to penetrate and reach the receiver, antenna, reflector, and revert back. So for that application we require some different type of material, germanium black polymer. And of course these materials are already designed in such a way that it has to face different type of environment. For example, from energetic oxygen plasma and high energetic kilo to giga electron volt electronic cloud. So these layers are very precisely engineered and designed to cover all the satellite part. So what we are seeing is, for this example, for this particular example of satellite means spacecraft, we must know what is the thermo optical property ratio, since the major outer external requirement is thermally it has to be insulated, and the stability of the material both in ground and space storage environment, and the material should perform very specific functionality. For example, for the antenna it should be RF transparent, and the sheet resistance should be preferably it should be in the range of semiconductor range. For example, when we need to passivate the electron cloud which is available on spacecraft, so it has to be passivated. So for that purpose we need semiconducting range of sheet resistance of the entire outer surface. And the coating, film addition, mechanical properties, all those things also matters. And also it has to be tested for several different space environment. It has to be compatible for atomic oxygen and UV and so many things. So if we stack all the relevant required functionalities, so that we could able to engineer and think about multifunctional adaptive thin film layers. Of course the story is not end here, because in practical we are already seeing many practical difficulties of mentioned material. For example, if we take freshly brought germanium black polymer, we are already having the required thermal, optical, and absorptance, sheet resistance behavior, and also it is highly transparent. But what we faced in ground storage, once we exposed this germanium black polymer to the normal ambient environment, it starts degrading, means it is absorbing oxygen from air and it's oxidized. So initially the degradation start in microscopically, like micro cracks, all those things we have observed, but later macroscopically degraded, and the degraded germanium black polymer is not serving what we required. Especially sheet resistance is already become highly insulating, and the thermo-optical properties also changed. It is not transparent anymore. So this is the major work which I worked in Indian Space Research Organization as my doctoral fellowship. It looked like very simple problem, but it's a functional material. So when we are trying to solve, we faced so many issues, and finally, of course, we optimized, means we got the solution. What we got is, when we tuned thin aluminum oxide layer over germanium black polymer, and we try to see the effect of this layer as a function of thickness, and with several environmental studies. So finally, so this is the evidence. So here we can see very easily we can understand the after giving a droplet on germanium black polymer, it started degrading very easily macroscopically. Visibly, it is started degrading. But after giving a thin alumina layer, it actually not shown any sign of degradation. So this we have purposefully studied to demonstrate the work. Of course, after giving alumina thin layer, we have undergone all the required functional behavior, right from sheet resistance, thermo-optical, and including RF transparency, and the RF transparent behavior of the optimized layer is already within our required limit. So the losses of this additional layer is in our limit. So like this, we have optimized the work. So next, I wanted to show some interesting material. It's a aerogel for super insulation material. So this you maybe now remembering. I have shown the multi-layer insulation, but there are few environment where this multi-layer insulation won't work. For example, gaseous environment like Mars. So when we are trying to cover up the spacecraft with multi-layer insulation and try to send to the Mars environment, it may not perform very effectively due to the gas incorporation between the layers. So to avoid that, we started developing aerogel, means it's a silicon dioxide powder basically, and we developed opaque as well as transparent aerogel, because always telling thermo-optical behavior. So if it is transparent, the optically absorptance and the transparently emitting optical behavior will be completely different, so that we can alter all the thermo-optical properties. So this way we have worked and demonstrated. So this is a commercially available aerogel thermal wrap. So the aerogel are present inside the fabric, means fiber matrix. So the material we have arranged such a way, and we have demonstrated how much we can implement this material. So but the major problem here, actually it is not a problem, but if we see in the thin point of view, making this aerogel as a coating is highly challenging because of super hydrophobicity. So this material won't stable on any surfaces. So that is the major challenge. So still now I was telling about some germanium black polyamide and some MLI. So both are, it's a fixed alpha and emittance, means the thermo-optical property is fixed. So once we tune everything, so we are sending the satellite and it's over, means it cannot be altered further. But what about if we have a smart material? If we have a smart material, when we are facing sun, it has to be the emittance behavior should be very high. And if we are facing cool, and if we are able to get some the alterating behavior of smart material is the next work what we seen. So it is already available as electrochromic and thermochromic material in day-to-day life. Maybe few people might have come across this. But what is the advantage? So we can actually eliminate all the active elements of in the spacecraft are also in the terrestrial application in a very way. So I told about optical solar reflector. So when we place the optical solar reflector, we have to keep an additional heating element inside. So instead of optical solar reflector, if we have a smart material, so it's very interestingly we can reduce the mass of the satellite. So it will have very good advantages. So with this idea, we have further started working in this way. I just wanted to show you one interesting example. This is the electrochromic glass, means smart window with electrochromic glass. So they have demonstrated by conjugating with solar cell. They have used the electrochromic glass as a storage material, means like a battery, and demonstrated with glowing LED. Of course, the electrochromic smart window is very costly because of multiple layers, including electrolyte, and so many layers are there. Of course, these are all now in research, but of course, I hope soon everything will be available. But here, after this, I wanted to introduce another interesting material. This is vanadium oxide material. So here we can see it's a single layer coating can perform thermochromic coating. And also many times, of course, including our group, we have reported vanadium oxide as the anti-reflecting coating. It is also researched for electrochromic behavior. Vanadium pentoxide is very famous in battery applications, electronic switches, and also we have seen the RF transparent behavior of vanadium oxide, and there are several reports about microbolometer, because it's very interesting. It is actually performing different functional behavior. So I hope there will be some meeting point to do many things with vanadium pentoxide material. So what in the literature, this is one very interesting structure. With this vanadium dioxide layer, they have demonstrated the IR twinning, means as a function of temperature, the emittance property is changing. Here, this is also very interesting. This is vanadium porous film. They have embedded in between two glasses, and they have demonstrated when it is hot, the IR is reflected, and when it is cool, it started allowing. So this demonstration of in automobile is very interesting. So soon those smart material can be, I hope it will be available soon in day-to-day application also. In this sequence, we have done research with vanadium oxide, molybdenum oxide, smart material, and we have seen the substrate dependency of the material. So when it is coated on quartz, it is moderately transparent, and when it is deposited on silicon substrate, it is showing anti-reflective behavior. And we obtained thermochromism in the temperature range of 50 to 60 degrees centigrade. This is one of important results what we got still now. Of course, there are few more challenges to make the coating as a final product, and we have done a lot of study with this, and I can show. For example, if we have only vanadium oxide, it's in amorphous state, and we achieved a transition temperature in the temperature range of 340 degrees centigrade. When we compose it with molybdenum oxide, the transition temperature drop down to 45 to 50 degrees centigrade, and if it is composited with titanium oxide, it is moderately we got between 44 to 48 degrees centigrade of transition temperature. Of course, from this we have understood this tuning of transition temperature also basically a big challenge for us. And as soon as the transition temperature is dropped down, we observe the transmittance compensation also. For this vanadium tin oxide composite is showing very less transition temperature, but we have lost the transparency of about 35%. And further, we have seen as a function of oxide, we have seen the sheet resistance and other thermo-optical properties also. The IR emittance values are very interesting here because it is the film deposited on quartz. It is highly transparent at room temperature. So we are actually reporting the quartz glass IR emissivity. in optically transparent. So it's very fascinating, but it's very challenging, as I already mentioned. um, okay, with this I can explain. This is the photonic elements. Here we can see active photonic devices. All those things are made up of oxides and optically transparent material. But here we can see the transistors, the gate, all those things are made up of conventional electronics, which is situated in planar. What if we have a transparent gates and switches, logic gates, all memory devices, everything in optically transparent, so we can actually incorporate inside the active photonic devices itself. So by this way only we can actually achieve complete smart window as a transparent. So of course we have several options of oxide materials. In this we can see traditional oxide materials with the different sheet resistance or conductivity ranges, ITO, and so many other material. But if we take each and every oxide thin films, the switching behavior is completely different. For example, vanadium oxide is switching behavior is considered as simple redox. But still now we are conducting many experiments whether it is ionic diffusion based switching or conductive, means it's a conductive resistive behavior. So this kind of different type of switching behavior is giving so much challenge when we are trying to make multiple layers and make a final device. Further, this switching behavior is also very important when we are making a transparent electrode to the material. So the formation of different junctions also very important, because when we are working in nanometric range, this junction formation and different switching behaviors are highly challenging. So in advanced stage, people already demonstrated transparent thin film transistors developed on both the polymeric substrate and also glass substrates. Here we can see functional layers of yttrium oxide and zinc oxide with the conducting material of ITO. Of course, as we are seeing here, the characterization of individual transistors are always challenging. In the transparent electrode field, there are so many material already available and being researched. The first important material is ITO and thin silver layer and graphene, carbon nanotube. So many are there. But of course, if we see in the chart, the ITO is a very good material which is not compromising both transparent resistance. When we are going for very thin, ultra thin metal layers, we have to compromise the transparency. So further, in this table we can see ITO as an anode and cathode is found with maximum luminance in the quantum LED conjugation, and the lifetime also reported very high. In the reported lifetime, this is being very high. But this is not related to transparent electronics, but this is the one important issue when we are bringing two different material to the electrically connecting, maybe by soldering or by deposition. It is forming always intermetallic compounds by diffusion, and so many other factors are also involving. This is greatly affecting the electrical conductivity in the micron scale or in nanometric scale. In this way, people already started working on metallic glass thin films as a solution. So metallic glass thin film, it's an amorphous in state. What we are believing now, and we are planning to start new work on with metallic glass thin layer, which can compensate both transparency and give good conductivity, and also perform as a diffusion barrier layer, which will avoid the intermetallic compound formation. In the ITO series, we have already done some work. This is very interesting work which I would like to share with you people. We have taken a FEP, fluorinated ethylene propylene flexible substrate, and we with collaboration we have developed ITO on the layer. Of course, we faced a lot of addition problems. So the work is demonstrating the before etching and after etching. The FEP is etched with plasma with the optimized time duration, and then we have seen the coating addition is very high, which is also slightly altered the transparent absorptance wavelength. But of course, we got in the full wavelength range, we got very good transparency. So this why this example is important. Sometimes in the practical application we may require very good addition of the film rather than getting very good transparency and also optical properties. The developed coating already tested for several space environment like the thermal cycling and thermo vacuum cycling, and we have seen the altered sheet resistance within the range with which is required for our space application, and the thermo-optical and transparency behavior also we have achieved. The maximum transparency required for this kind of coating in spacecraft is 8%, so that we could able to achieve. So here we can see the comparison of ITO coating on different substrate, FEP, Kapton, and aluminized Kapton. These things also been optimized for several applications in spacecraft. Because the transparent electronics is not only on rigid substrate, sometimes we may require on polymeric substrate also. So by which we can use the complete device as a wearable electronics. So in that motive, we also should concentrate on flexible substrate. So here is the challenges. The first challenge is starting from the substrate. Of course, that substrate should be very transparent and should be CMOS compatible. The electronic conductivity of the substrate also very important, that I already discussed in detail. The processing compatibility. Here it is very important to talk about processing compatibility. For mass production, many demonstration is already available. Quantum dots being synthesized and transferred by inking and printing process. But the problem here is the substrate and also the chemical involved in quantum dot means any nanostructure should be very compatible. So sometimes for mass production, people are mostly concentrating on spin coating, thermal evaporation, and ink pen printing. So the material which being developed finally should be available and compatible for mass production also. Of course, as we already know, making the proper electrical conduct between quantum dots and carbon nanotubes and any other thin film, especially oxide thin films, is very challenging task. And actually, I am planning to work further on that matter. So when we are coming to characterization challenge, of course, it's a very big field to talk. Right from scanning electron microscopy till very advanced secondary ion mass spectroscopy, scanning tunneling spectroscopy, so many things we can perform on functional materials, especially oxide layers. The first major problem is beam sensitivity. When we try to prepare the sample by FIB or some other exposed to SCM and even TM also, we are always facing beam sensitivity. And the next is we observed the developed layer is not uniform entire the thickness. It may show always gradient oxide states. The surface oxide state is always stable. So when we try to see the surface oxide state, we cannot determine that is the overall thin film oxide state. So this is also one important challenge. So XPS is normally used for surface oxide state, and but normally this is for when we try to use XPS for depth analysis, it required a lot of expertise in that field. When we talk about functional behavior is directly dependent on substrate. We have already seen when the oxide thin film deposited on quartz, it's showing completely different behavior, optical behavior, and when it is deposited on silicon, it showed anti-reflective behavior. So the functional property is directly depend on substrate. so which needs to be taken care very precisely before starting any characterization, especially sheet resistance measurement. The sheet resistance measurement, we have seen the ionic conductivity of layers between oxide layers and the substrate also placing a major role, and also the some contamination effects also we are seeing more effect on in sheet resistance measurement. And water contact angle measurement is the important when we are talking about stability of the coating and many other hydrophobicity, that kind of behavior we can easily see by water contact angle measurement. That in that we are not facing any problem. But when we are talking about thermochromism of material, the temperature dependent emittance property of thin film is very challenging. Few reports already available with synchrotron radiation. With that experiment, they have demonstrated temperature dependent emittance property, which is not available for normal characterization. And so that we are trying to get the get the property details by sheet resistance, temperature based sheet resistance, or optical measurement, and so on. So emittance measurement is still a challenging thing. When we come to diffusion and intermetallic behavior, we have few options, which I am going to talk in detail for SIMS. But the scanning tunneling spectroscopy is very interesting. But the problem is they are using epitaxially grown layers inside, means in situ they are developing the structures and doing studies. So these methods are not yet to be realized for practical application. Means suppose if I have a substrate with some layers, and if I want to measure practically what is the performance of the electrical performance of the layers, it's very difficult to do by STS. And there is another one new concept is called depth composition analysis by PES, which is not my field right now. So among this, what we understood is studying functional material TM is very interesting. So in this motivation, we have started working on in situ TM, small angle electron diffraction, and yields, all those things. In situ here it means actually we can perform many in situ characterization, but what we first taken as taken is temperature based TEM studies. What are other in situ studies are oxygen, or oxygen in the presence of gaseous environment, or sometimes electrical in situ electrical measurement are also being performed. But as the function behavior, what we are now seeing is temperature dependent, so we have concentrated on this. So for in situ TEM measurement, the sample preparation is highly challenging. I think many of you know there are two major sample preparation methods available. One is focused ion beam, and the next is electrochemical polishing. But reproducing the similar features, the exact thickness, and so many other challenges are already available. I mean, already being reported. The another important challenge is problem is reported is amorphization. Suppose if we have a crystalline structure, and it will partially it will convert into amorphization, amorphous state, and the structural and oxide state modification also sometimes reported, because we are estimating the oxide state of the material after undergone FIB and doing yields and other studies we are doing, so that what is the impact of beam on the sample, that is a major concern here. There is another deposition method. There is another method. It is direct deposition. But the straightforward problem here is cross-sectional sample is not possible, because suppose if I have a thin film on silicon or glass, the entire structure cannot be studied. But of course, the individual layers can be studied. So another concern for this deposition is the environment. Suppose if I'm using high temperature deposition method or chemical environment, so these things may affect the platform, means the sample platform of for TEM study. So this is the prototype which we have taken. means which is being used for temperature based in situ TM. Here we can see the platform, which is a 9 window. Uh, why we okay, first I will explain what is the background of the work. So we have a prototype, so we have different windows, which the prototype is also costly, and sometimes we may have to repeat the experiment many times. So if we are able to get the sample precisely on the sample surface, it will be really interesting. For example, the deposition environment is directly affecting this prototype. Here we can see the electrical conduct. Majorly this electrical conduct, if being damaged during sample preparation, it's very difficult to uh, further continue. So with all this consideration, we have given copper grid and kept on another layer. Means it's a double masking we have given, and chosen two specific window, and used this setup for to develop vanadium oxide thin film. And this is the graphical illustration of how we can get deposition of a very small region layer on the specific part. So in this optical microscope image, we can see this window is approximately 30 micrometer. So this demonstration having so many advantages. First is highly reproducible. So once we tuned the thickness, we can many times we can develop the similar material for many different type of studies. Then next is no beam damage, because vanadium pentoxide is known for ion incorporation, because it's a battery material. So without beam influence of FIB, for example, so we could able to synthesize the sample on the precise location. Possible to vary composition gradient sequence. Suppose I just want to see some minor variation of thickness, or else I have to give some composites, multi-layer temperature study. All those things are very easily possible by this sample preparation method. And easy thickness optimization, this is always being considered. Suppose if I prepared a sample that may be electron beam transparent, but sometimes it may fall under geometric blurring. So when we try to see the very minute features, so it is may not be possible. So we require minimum thickness, which is also should be electron beam transparent. With this compensating optimization, all those things is possible by this method very easily. And especially for in situ studies, the 2D planar view is very very important. So this is actually possible by this direct deposition method. So we demonstrated this setup by doing one in situ study. This is the vanadium oxide thin film directly coated on the, by using this method we have coated on the prototype, and this is before heating, this is after heating. Add of images. Then we have seen small area electron diffraction. First it is completely amorphous. During heating, this is at 500 degrees centigrade, we observed the formation of monoclinic VO2 and mild monoclinic V2O5 crystalline nature. Upon cooling, we observed the structures is in stable condition. Means vacuum heat treatment of vanadium oxide amorphous layer is directly influenced to form monoclinic VO2. Later we understood formation of monoclinic VO2. It's a very tough task, because in phase transition theory, monoclinic VO2 is majorly considered, and synthesis of pure monoclinic VO2 is also is a challenging task. That also we have demonstrated with this work. And this is the one typical example of electron energy loss spectroscopy, which is taken at 300 degrees centigrade. So this work is yet to be published. So many work is going on parallelly in this, but I can brief about electron energy loss spectroscopy. This is the direct method. The prepared samples oxide state can be very clearly uh, obtained by electron energy loss spectroscopy. This is a very interesting method, but it is also highly thickness dependent. So for electron energy loss spectroscopy, we may require around 5 nanometer of very thin coating. So with this challenge, actually we worked to find new different method of sample preparation. With this demonstration, we are hoping in future 2D electronic devices also can be fabricated on prototype directly with planar view, of course. We may additionally add lithographical technology to prepare very specific structural mask. With that, we can actually do many more in situ TM characterizations. The next important characterization method which I wanted to show you, discuss with you is secondary ion mass spectroscopy. So already I explained about X-ray photoelectron spectroscopy. This is the vanadium pentoxide surface XPS. Here we can see vanadium pentoxide is as a major means V5 plus as a major oxide state, and with some minor vanadium dioxide state. But this is not true when we see by SIMS depth profile. Means SIMS secondary ion mass spectroscopy is a ion beam etching process. It will completely etch throughout the layer, and as a function of depth, we can understand the layer structure. But in this report, they have clearly reported the outer layer is actually higher oxide state, but the internal layer near to the substrate is actually mixed oxide phase or very reduced oxide phase is reported. And also the diffused OH and fluorine from FTO, means in this paper they have worked with FTO, glass and vanadium pentoxide layer. So fluorine also diffused into the thin film layer. Another problem with SIMS is, of course, it's very powerful tool. We can get very minor contaminations of thin films also. Here they have shown from sodium, magnesium, silicon, very minor diffusion into the thin film also they have discussed. But the problem is, when the argon ion beam is interacting with the oxide, any type of oxide layer, it reacting and splitting the oxides into several different oxide states. So what we are actually seeing is with that data we are unable to determine the exact oxide state, or composition depth we cannot determine by SIMS. This is the major disadvantage of SIMS. So many times people are combining both XPS surface spectra, at least to understand the surface, and then taking the secondary ion mass spectroscopy. With the secondary ion mass spectroscopy, already some functional behavior is demonstrated. For example, lithium ion intercalation and sodium ion intercalation also has been demonstrated. So there are several challenges are already available, which I tried to cover up in this. But in conclusion, I wanted to tell, of course, we have a lot of challenges, but we have to take up all the challenges to realize our future of smart windows, sensors, touch screen, and so many things. And I believe transparent integrated processors, circuit display, sensors, everything will make our future very newly, and can be completely replaced photonic systems, which is also very important. With this all advancement, we can try to realize zero energy required environments. Now presently we are working, my major work is on smart thermochromic material and its physics. In parallelly, we got very interesting result for transparent semiconductor switches development, and smart thermoelectric generator on window glass. So these two are in parallel. Of course, I could not able to explain further because the transparent semiconductor switches, this development is now patent. The patent procedure is going on. So further, I am unable to explain in that. I hope in near future I can explain still more. Research is future, but we should always know the present requirement and the necessities. So with all together, we can make our future very beautifully. I hope this presentation and this talk must be very informative to you. Of course, I try to uh, minimize many things and try to give very important technical insight to you. Um, so, if you have any questions, now we can go ahead.
Thank you, ma'am. Now,
Yeah.
I request dear participants, if you are having any if you need any clarification or if you're having any doubt, you please ask. Please unmute yourself and ask directly to our resource person. Ma'am is waiting to give you answer. Or you can type your question in the chat box. We will ask on behalf of you.
If you don't have any questions, at least you can try to give some feedback also. Maybe it will be
Yes,
really useful for my further
I, re-
continuing research.
I request dear participants, you can give your feedback on our session.
Hello, good afternoon, madam.
Yeah.
Yeah, this is Naresh from BITS Plan Airport Campus. Research.
Yeah.
So it's a very nice presentation, madam. Actually,
Yeah.
information was there in the presentation.
Okay.
It is an honor to listen to you, madam. So I got one simple query, madam. So TEM is the transmission electron microscopy.
Yeah.
So generally, my study is uh, passive cooling of buildings by using phase change materials. Phase change materials.
Okay.
So
Mm-hmm.
in that, to incorporate the PCM material in the buildings, I'm
Mm-hmm.
preparing micro PCM, micro encapsulated PCMs.
Okay.
So I would like to show the core shell structure. Means it is covered by shell. PCM is covered by shell. So I would like
Okay.
to show that by using TEM, transmission electron microscopy.
Mm-hmm.
So
Mm-hmm.
can you please suggest any other simple method which can be used to show the same features?
Okay. It's if you need nanometric features, then there is only one possibility is TM only. And this is very specific question actually. If I know further, maybe you can take my email ID and you can definitely contact me. I can, if how much is possible, I can give some very good suggestions to you.
Sure,
And
madam.
we have also people who is working with TM in India also in my collaboration. So
I will take your mail ID, madam.
yeah,
So
sure, sure.
thank you very much, madam. This was
Yeah, I'll do.
thank you.
Thank you, ma'am. Dear participants, you can type your questions in chat box also. We will ask on behalf of you. Ma'am, in chat box, we are getting overwhelming responses, positive responses, ma'am. Thank you, ma'am.
Thank you so
Very
much.
positive responses that you can see on chat box, madam.
Yeah. Yeah, actually, thank you so much for everyone. Uh, I must leave now. So actually, you people have given me 2 hours time, but I could able to take only 1 hour due to my time limitation. So if it is okay for you, then I must leave now.
Ma'am, just 2 minutes, ma'am. I will conclude with
Yeah,
the vote of
yeah,
thanks, ma'am. Please, ma'am.
yeah, yeah, sure. Yeah, yeah,
Uh,
sure, sure, sure.
Thank you for your wonderful presentation, ma'am. Your presentation added more value for this short-term training program. Really, it is excellent presentation, ma'am. You are given good knowledge about oxide film and characterization, which are useful for all the participants and particularly for the research scholars who are currently doing their research. The takeaway from your presentations are very high. You have started with the functional behavior, a passive thermal control, multifunctional adaptive thin films, Y functional behaviors, and optical RF transparent protective alumina thin films, silicon oxide, aerogel for a super thermal insulation, and classification based on requirement of external energy, and vanadium oxide coating in automobile application, vanadium oxide composites and its comparison, the future of functional metal oxides in display technologies, in photonics or optical communication, and single chip microprocessor that communicates directly from light, and transparent electrodes, metallic glasses, and transparent thin film transistor using oxide semiconductors. Then characterization advantages and direct deposition. In future, you told that 2D electron devices can be realized on photochip by employing masking method. Finally, you conclude with secondary ion mass spectroscopy and your research work. It is a really excellent presentation, ma'am. Now, I request our convener to conclude this session with the thanks to our resource person, Professor Chandrasekhar sir.
Can you take 1 minute?
Madam, good afternoon, madam. Hello.
Shall I take 1 minute in between?
Yes,
you
ma'am.
go.
Yes, ma'am.
So I also must thank all the organizers and participants. And here I would like to thank my supervisor Arjun Day from ISRO and Dr. Dinesh Rangappa from BTU, and many of our colleagues in ISRO also who helped me to achieve all these things. And now I'm in Germany because of everyone. I must thank everyone. Thank you so much.
Thank you, ma'am. Professor Chandrasekhar Reddy sir, please. Sir.
Is it audible, sir?
Yes, sir. Yes, sir. Audible, sir. Audible.
Yes, sir. Good afternoon, madam. On behalf of management, principal, Department of Mechanical Engineering of SVCE, and participation and delivering an informative and thought-provoking webinar on functional behavior of oxide, thin films, and characterization challenges for smart and futuristic applications, organized by College of. In spite of your busy schedule, thank you very much, sir. Thank you very much, madam. And your reference is given by the Narendra sir, who is working in CMTI.
Yeah.
And also, I'm also thankful to the Narendra sir, madam.
Okay,
Thank you, madam. Thank you very much.
Thank you. Thank you.
Thank you. Yes.
Thank you, ma'am. Thank you. Dear participants, our afternoon session ends here. Our tomorrow session will start as usual 10 a.m.
Sir, 1 minute, Madhivanan sir.
Yes, sir. Yes, sir.
Madhivanan,
Yes, sir. Yes, sir.
is there
Please.
any possibility of introduction of the participant to the other participants? If possible, we'll take 10 minutes of their time.
Okay,
because
sir.
we
Okay.
have to know each other.
Yes, sir. Yes, sir. Yes.
Because every day we are meeting in the online, but we don't know who are attending. I think
yes,
it's a good idea. Can I go ahead like that, Madhivanan sir?
Sure, sir. Sure, sir. Now I request, dear participants, we know that all are professors and research scholars. You can introduce yourself and you can share your research work also. That will be useful. Yes, sir. That will be useful for other participants, and we will get to know that among ourselves. I request, dear participants, professors or research scholars, you can share. You can introduce yourself and share your some research work that will be useful for participants also. Requesting, sir.
Hello, good afternoon, all of you.
Yes, sir. Yes, sir. Please.
Sir, good morning. Good afternoon, sir. Myself, Yogesh Dubey from Jaipur. Actually, I am assistant professor and I am planning to do research work in the welding purpose, in the welding field. So that's why I am looking for this FDP, and this is very useful to me.
Thank you, sir. Thank you very much, sir.
Okay, sir. Thank you.
Sir, in welding, which area you are planning, sir?
Actually, I am planning for the TIG, MIG, and general arc welding, and sometimes maybe if everything goes good, then I will go for the laser also. Actually, right now I'm the research scholar.
Thank you, sir.
Okay.
Thank you very much, sir. Thank you, sir.
Welcome, sir.
Dear participants, please, you can introduce yourself and you can share your research work or the status so that other participants will be get benefited. Requesting, sir.
Madhunan sir, start from
Ah, yes.
ourselves. Start from ourselves.
Okay, okay, okay,
First,
okay.
we'll
I'll
introduce ourselves. Yes, yes.
okay, sir. I'll start myself, sir. My name Madhu Anand, associate professor in Department of Mechanical Engineering, Sri Venkateshwara College of Engineering, and we are doing a research on friction stir welding. We have completed, and we are going for planning to do in the nanomaterials also. That's why we are conducting and attending this program very eagerly, very expecting some more information from this. And we request our coordinator to introduce ourselves. Um, Sir, Rajesh sir, are you there, sir?
Sir, I'm available, sir. Thank you, sir.
Please, sir, please, sir, please.
Sir, I am Dr.
Sir.
Rajesh, and I am.
Yes, go
Sir,
ahead.
shall I
Go ahead,
proceed?
Rajesh.
Okay, okay, sir. Okay, sir. So I have finished my doctoral degree in nano composites from JNT Anantapur. Thank you, sir.
S-
Madhunan sir, I will go ahead.
please, sir, please continue, sir, please.
Yes, yes. Myself, Dr. M. Chandrasekhar Reddy, and I am convener of this program, and I am heading the Department of Mechanical Engineering, SV College of Engineering, Tirupati. And myself, I have completed BTech from PS College of in Bangalore University, and MTech from JNT Anantapur, the University College, and a PhD from JNT Hyderabad in the field of nanofluids. And currently, I am guiding 4 research scholars in the field of, one is in nanofluids, another one is composites, and remaining 2 are also in composites field. And presently, I am heading Department of Mechanical Engineering, SV College of Engineering, Tirupati. Any other, please?
Hello,
Yes, ma'am. Yes, ma'am. Please.
myself Snehal Joshi. I am working as associate professor in physics in Kekewag Institute of Engineering Education and Research, Nashik. My interest of research topic is the solar cell, and that's why in the morning I talk about the anti-reflection and coating and etc. Thank you, sir.
Thank you, ma'am. Dear participants, you can introduce yourself and you can share your research work, research topic that may be useful for the participants.
Good afternoon, sir. This is
Yes, sir.
This is Dr. Vamsi Krishna from Mechanical Engineering Department from the Sri Venkateshwara College of Engineering, Tirupati, from the same college. So my PhD in the year of 2017 awarded on the title of Composite with Aluminum Silicon Carbide on steel casting materials. So now I am extending my work towards the nano level. So now the trend in aluminum has seen the aluminum zirconium composites. So my next level is with this STTP, I plan to work on nano level on a aluminum zirconium composite, which is aluminum of 5 series. 5 series aluminum mixed with zirconium. Together, I'm going to study its nano level mechanical properties and hardness and other things. So this STTP helps me to think in depth about my work. So this is very I would like to thank my HOD for giving an opportunity for us to enhance knowledge on the nano level of the materials. Thank you, sir.
Thank you, sir.
Hello.
Yes, sir. Please, sir.
Hello. Am I audible?
Yes, sir. Yes, sir. Please, sir. Please proceed, sir.
Yeah. I am myself, Dr. Arun, from working as a head of the department in Government Engineering College, Haveri, in Karnataka. So I have attended your past one's series also. So it seems effective. And myself, I have done my doctoral degree in the year 2007. Basically, I am from fracture mechanics area, fracture and fatigue, and started working on nano composites. And presently, I'm working on nano blended composite coatings by pulse electrodeposition, CVD, and the characterization of those things based on a VR, and especially expertised in microscopic techniques. So this has helped me a lot to increase my knowledge, because you found basically I want to say congratulate, or I want to say put my gratitude towards the organizers. Is say you have selected a very good speakers. So they have spoken very well speakers, and information conveyed by them is highly appreciated. Even though I am into field, I am into in this field from past 15 years, but many things are unknown, and I gained, even though I have guided many scholars and I am guiding many scholars. Even after that, I have taken some knowledge out of your course. So it's a beautiful speakers what you have selected. Thank you, sir.
Thank you, sir. Thank you very much, sir.
Hello, sir. Good afternoon. Hello.
From Naresh, go ahead.
This is Naresh from BITS Pilani Arbeit Campus, Research Scholar.
I know very well you.
Thank you,
For
sir.
past 4 sessions over attending.
Yes, sir.
Go ahead, Naresh.
I'm attending this fourth session also. Continuously,
Yeah,
I'm
yeah,
attending all the sessions. I'm very
So
much
thank you,
happy
thank you.
and knowledgeable. I'm gaining so much knowledge from these sessions. And speaker selection was very good, as others also mentioned. Thank you very much for this opportunity, sir. I'm attending this all this STTP because it's advanced technologies, and I'm going to get some input so that will be helpful for my research. I'm attending this session, sir. Really very much knowledgeable session, sir. Thank you very much for the opportunity.
Thank you,
Thank you,
Naresh.
sir. Thank you, sir. Thank you, sir.
Thank you. Hello, sir.
Sir, please, sir. Proceed, sir.
Can we have the email ID of the previous speaker, sir?
Sorry, sir. Email ID of the
Just previous speaker, sir.
okay. That afternoon speaker, no?
Yes,
Ma'am.
sir.
Okay, sir. Okay, sir. We will share to you through mail, sir.
Yes, sir. Please, sir.
Uh,
Thank you. Thank you.
Hello.
sir. Yes, sir. Please, sir.
Sir, myself again, I am Dr. Arun myself.
Yes,
So, sir, I request you organizers to at least arrange one session, if possible, on reading of this SEM scans, TEM scans, and all.
Okay,
Because
okay, okay.
now young researchers, many young researchers, they carry out the experiments later on based on looking at the journal papers. They just go and take the SEM scans, and as we see in the, since I am into editorial member or editorial board of a number of journals, when we review the papers, there won't be any discussion on SEMs. They simply just as shown in SEM. But the thing is, SEM has got some information. Say where below that SEM they give WD ratio, a line, a theta. So what exactly it means? Like that, if you arrange anybody, see, you let them speak at least for some 30 minutes or like that in such 0 hours. so that researchers will be benefited out of that. Maximum researchers. If possible, you please arrange it, sir. If
Oh,
possible.
okay. Yes, sir. Yes, sir. Yes, sir. We will
Thank you, Arun,
consider.
sir. Arun, sir, thank you very much for your opinion.
Sir, because it will be benefited to many researchers, sir, young researchers.
Yes, sir. So last
sir.
three, I think Madhivanan sir were covered in second or third.
So first STTP itself we have covered, sir, with the CMT resource person.
But that one, what has been given, no, sir. So it is a it's just an explanation of those scans they have given.
But yes, sir. Yes, sir. Yes, sir.
But reading of SCMs is different from that, no, sir.
Okay, sir.
That is possible because everybody is going for SCM, TM nowadays. Earlier, when we have done our doctoral degrees, SCM availability was rare in 2006-7. But now SCMs are available everywhere and people are going for SCMs. But the discussion part of that, we find a scary discussion, a lack of discussions in that SCM with respect to, especially with respect to relating the data with SCM, graphs and SCM and all. So, so if possible, that is my request, so that people will get benefited out of that.
Okay, sir. Sure, sir. Sure.
Okay. Thank you, sir. Thank you.
Thank you for your session, sir. Thank you, sir.